All right. Now, guys, we have totally been talking about evolution and the concept of genetic change over time. So what often comes up as a question is, hey, how do we find out if evolution has actually occurred? So what we're going to do is take a look at math, yay, we love math, a mathematical way of evaluating whether a population has evolved or not. So some concepts that we have to remember when we're taking a look at that is, what's a population? Okay? And a population, you'll remember, same species, same place, same time, and our favorite, they interbreed. A gene pool is going to be a collection of all of the alleles in the population. So go back to your brains and try and remember the difference between an allele and a gene. I'm not going to tell you, I'll have you tell me tomorrow. What's going to become important is the frequency of the allele. So how common is that allele in the population? How many big A's, how many little a's? How many big B's, how many little b's? How many big R's, how many little r's? Evolution will occur in a population, and we'll be able to see that if we see a change in the number, a change in the allele frequency in a population. In order to be able to mathematically measure that, we need to have a perfect system. A hypothetical, hey, what would it be like if allele frequencies didn't change? And some gentlemen, Hardy and Weinberg, came up with 5 conditions that would need to exist in our perfect allele frequencies not changing situation. A non-evolving population needs to be very large. In math, and especially in statistics, the bigger the sample size, the more accurate our measurements and our results. So, very large population size, no genetic drift. Remind ourselves, genetic drift is most disastrous, so to speak, or has the biggest effect on a very small population. No migration, no movement in, and no movement out. Remind yourself which one is immigration and which one is emigration. No mutations, no genetic change. What's the likelihood of that happening? Random mating, no sexual selection, and no natural selection can occur. So we ask ourselves, if we want to find out if the population has evolved, often has natural selection occurred, we take a look at it from the null hypothesis perspective of, hey, what would it look like if it did not happen? So a mathematician and a physician got together and they came up with a mathematical way of evaluating a population to figure out if the population has evolved or not. Stop. Now, we do not want to freak you out when you think, oh no, I have to do math and I have to look at a population in terms of math. There are 2 equations and 5 total terms that you're going to need to know to be able to do Hardy-Weinberg problems. So, to not freak out, let's identify them. We have P, which is going to be the frequency of the dominant allele. We have Q, which is going to be the frequency of the
recessive
allele. Very good. Yep, recessive allele. And our frequencies are usually, given to us as decimals or as percentages, which we then convert to a decimal. We're then going to look at, these are going to be genotypes. We're also going to have P squared, we're going to have Q squared, and we're going to have 2PQ. P squared is going to be the frequency of the homozygous, what? Homozygous
allele, dominant allele,
homozygous dominant, Yay. What would Q square be then? The frequency of
Recessive allele?
the homozygous recessive.
Oh, homozygous.
Homozygous recessive. And then 2PQ is going to represent the heterozygous.
Oh.
These 5, if you know these 5, you are set. P, Q, P squared, Q squared, and 2PQ. The other two parts are very simple. P plus Q always equals 1. And P squared plus 2PQ plus Q squared equals 1. What will happen as we work Hardy-Weinberg problems, which we're going to do after this, you will be given one of these 5 conditions. You will be given either P, Q, P squared, Q squared, or 2PQ. And you'll be asked questions about finding the rest of them. So, we're going to be doing some word problems like you've done in math and know and love so well, and we're going to apply them to genetics and natural selection to determine if the population has evolved. If we know the frequency of an allele at the beginning of a period of time, and we want to know if the population has evolved, we will calculate the frequency of the allele at another point in time. If there is a change in the frequency, the population will have evolved. All right, let's just do a sample problem before we go on to do the ones that will be your homework. We have a population. Here's our little baby kitties. We have 100 cats. We have 84 black cats, and we have 16 white cats. I want to know how many of each genotype, how many homozygous dominant black cats do I have, how many heterozygous cats do I have, and how many homozygous recessive cats do I have. In this situation, our dominant allele, big B, is for black fur. Our recessive allele, little b, is for white fur. Okay, we know we have 84 black cats and 16 white cats. We know one of these 5 things. We have been given either P, Q, P squared, Q squared, or 2PQ. What have we been given?
I think the Q squared.
Yes, we have been given Q squared. Okay, so Q squared is equal to 0.16, 16 over 100. So if Q squared equals 0.16, what can we get from here then? What would Q be? How would you find it?
I don't know.
You would take the square root of 0.16, so 0.4.
Okay.
If we know Q, what can we find out?
P.
We can find out P. So what's P?
0.6.
0.6. Very good. What we want to do now is how many big B's do we have?
Square that, right?
0.6 times 0.6 is
0.36.
0.36, so we have 36 big B's. How many big B, little b's do we have?
36 minus 84?
36 minus 84, very good. And how many white cats do we have?
16!
16, because you have been given that.
Yes.
Now, what I'm going to do is give out some problems. We'll take a look at those and work on solving some more Hardy-Weinberg problems.